All right, welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. I know you're all super keen to get out and start doing some hypothesis testing, but before you do that, you have to realize that if you're going to do lots of hypothesis tests, you have to correct for multiple testing, and that's what we'll be talking about in today's lecture. All right, so what we'll be doing today is discussing the Familywise error rate. The Familywise error rate is one way of trying to account for multiple testing corrections. Perhaps it's the most classical. What we're really just trying to say is, what is the probability of getting at least one false positive? And that's what we're trying to control for. Not the probability of getting a false positive, but at least one among multiple tests. So let's look at how we do that. And welcome back to another lecture of Stat 568, Design and Analysis of Experiments. Today, we'll be doing multiple testing. We're starting chapter 3 of my lecture notes. And it's going to be a very short one, but also a very important one focused on the idea of multiple testing corrections. So what in the world is multiple testing corrections? Well, the way I like to think about it is, imagine that I were to take 10 coins out of my pocket and then just throw them on the floor. Now, the odds that they all land heads up is a little bit over 1 in 1,000. It's 1 in 1024. So let's say 1 in 1,000 chance. It's pretty rare. Probably won't happen, but not unimaginable. Well, okay, now imagine there's 100 of us and we all take 10 coins out of our pocket and throw it on the ground. What's the chance that at least one of us will get 10 heads face up? Well, that becomes more like a 9.3% chance. So the idea is that, okay, the chance of a 1 in 1,000 event happening is, well, 1 in 1,000. But if you do that 100 times, it looks more like 9%. Or at least in the case, I should say, 1 in 1024 becomes about 9.3%. So the point is that if we do lots of hypothesis tests and we set a threshold for significant or for rejection of the null, like 1%, like 0.1%, or 5% if we really want to go with 5%, then what happens is, okay, we run one hypothesis test, that's fine. But if we run multiple hypothesis tests, there's a good chance that by dumb luck, we're going to see something that looks significant when it actually isn't. And that's the idea of multiple testing, or that's a multiple testing problem. And what we'll talk about is how to correct for multiple testing. Now, we already did this a little bit in some earlier lectures. We looked at two methods, the Bonferroni correction very briefly, and in more detail, we spent some time looking at the Tukey's post hoc Tukey test. And in that case, it's applied very specifically to a collection of pairwise t-tests, that is the post hoc Tukey test. In this section, we're going to be considering more general methods like Bonferroni, but more advanced or sophisticated than the Bonferroni method, which is often too conservative to use in practice. So let's take a look at that. All right, so the point is basically, just to reiterate in words what I was talking about, or in maybe numbers, is the idea of flipping coins, which is, okay, 10 heads has a probability of 1 in 1024. Okay, but repeated 100 times has a probability of 1 minus 1023 divided by 1024 to the 100th power, which is approximately 9.3%. As I mentioned in the kind of introduction here, So that's the rough idea that I was trying to write down or trying to say out loud, but now I can write it down in numbers. But in the case of hypothesis testing, let's say hypothesis testing, we'll say 1 false positive, type 1 error if you like that terminology, but I hate that terminology. So 1 false positive, we'll say, has a probability of alpha, whatever alpha is, 1%, 5%, 0.1%, 1 in 10,000, you know, whatever you want alpha to be. Then I think my notation is M, yeah. M, or I should say, makes this more precise. Then the probability of at least 1 false positive over, we'll say M tests. So in this section, M is going to be the number of hypothesis tests that we're performing. What the probability of at least 1 false positive over the M test is 1 minus 1 minus alpha to the M, which is typically much, much bigger than alpha. If M is equal to 1, you can see that everything kind of the ones cancel out and you're back to just alpha. But very quickly, you start to get, big numbers there, or I should say numbers that are bigger than alpha, the desired false positive rate or size or threshold for our test. All right, so then the question is, well, how in the world do we fix this, right? Well, there's one other thing that I also need to mention first, which is the, we'll call it the setup. And the setup is that we will assume that a p-value, let's say p sub I, is a uniform 0, 1 random variable under H naught, the null hypothesis, whatever the null hypothesis is. In this course, it's typically that the treatment has no effect or the block has no effect or whatever factor we're looking at has no effect. But in this case, we can actually generalize this outside of design of experiments. The idea of multiple testing correction can be applied in many, or in some sense all, areas of statistics where you do hypothesis testing, which is a big chunk of statistics. Now, in that setup, we typically say that if a p-value is, if we're living in the null hypothesis setting, then the p-value should look uniform 0, 1. Now, that's not always going to be the case. It's when you have, say, discretely observed data, but roughly we're just going to kind of brush over that for now and say that our p-values, our null p-values, are all going to be uniform 0, 1. And of course, they all have to be within the interval 0 to 1 in general. But strictly speaking, the null p-value should look uniform on the interval 0 to 1. And then after that, we get into this split. There's probably other ways out there, but we have 2 different ways we're going to talk about to control the error rate. The first is going to be called the family-wise error rate. The second is going to be the false discovery rate. We're going to save the false discovery rate for the next lecture, and today we're going to talk about family-wise error rate. That's going to be the focus today. So family-wise error rate, or from now on, it'll just be the FWER for short. Okay, so what is that? Well, the idea is that given, we'll say, M hypothesis tests, the family-wise error rate error rate is the probability that we reject any H naught. I'm going to write H naught I, which is the ith null hypothesis, right? We're going to have an H1I for the ith alternative and an H naught I for the ith null hypothesis. And that's given that H naught I is, well, I'm just going to write is true. If we really want to be kind of pedantic about it, it might not be the exact right way to say it, but effectively we're saying, let's assume that that null hypothesis is true. Then the family-wise error rate is the probability that we reject anything, any nulls that we shouldn't have rejected. That is equivalent to the probability of at least one false positive. So in the example, well, that's about to run off the top of the screen up there, right? If the example from above was that the family-wise error rate, if I do M hypothesis tests without any corrections for multiple testing, I would get a probability of 1 minus alpha to the mth power, which, yeah, if you work that out, it can be quite a lot bigger than alpha, even if, even if M is not large or not quite big. Right, so then the question is, how in the world do we correct this? Because the goal is to change our rejection threshold so that what? So that the family-wise error rate is less than or equal to alpha, the desired test size. So now alpha used to be just the probability of a false positive for a given hypothesis test. And what we really want is we want alpha to be the probability of at least one false positive. All right, so we want to make sure that if we run our 20 hypothesis tests, that the probability that there's at least one false positive is only alpha, which could be, again, 1% or 0.5% or 0.1% or whatever you want. And then there's a ton of ways to do that. So we're going to go through and talk about them all. The first one we're going to talk about is we're going to return to the easiest and classic one, the Bonferroni, Bonferroni's method. And what I'm going to write in the margin here is this is very, or maybe not very, because very is not descript enough. We'll say widely applicable. But because it's widely applicable, it is overly conservative. This is often the trade-off you get. The more information you have about the specific hypothesis tests you're running, the more of a specialized method you can use and the better results you can get. But Bonferroni is great because it's like a sledgehammer. You can just hit anything with it and it'll probably do what you want it to do. But it might be a little bit overkill in the sense that it penalizes too much and you are at the risk of not a false positive now, but a false negative because you're going too intense at the multiple testing correction. Right, so what does Bonferroni's method say to do? Well, basically simply replace the, we'll say individual test size alpha with alpha divided by m. So, for example, if we're running 10 tests and alpha is 1%, then the new I guess, size or level to reject that, but we also talk about factor levels, so I'll use size for this, is basically 1%, 0.01 divided by 10, or 1 in 1,000. So we just move the decimal place over 1 point. So why does that work? It seems like it might make sense, but why should we trust that? Well, the idea is that if we write it out, we can say that the family-wise error rate mathematically now, forget about the words that I wrote above, let's do proper math notation, is actually the union. I'm going to need one more notation here that I forgot to write down. So we're going to squeeze that in here. And I'm going to write it in blue because we're going to use this same notation for the rest of the lecture. So it doesn't just apply to Bonferroni, it applies to everything we're going to do here. And the notation is that we'll say we have I naught is going to be a subset. It's going to be a bunch of, well, numbers between 1 and m. It's going to be a subset of that. I guess it could be the entire set, or it could be a proper subset of those, that finite collection of integers, such that h naught I is true for I in I naught. So basically I naught is the set of all the indices for the nulls that are true. That makes sense, right? So it could be empty. Maybe none of the nulls are true. It could be the entire collection of M hypothesis tests. Maybe they're all true. There's absolutely nothing interesting going on here in our experiments. Whatever it is, it's just sort of a mathematical notation saying these are the indices that correspond to the null hypotheses that are true. Now, given that notation, we can then write the family-wise error rate as the probability over the union of I, little I in I naught, capital I naught. And we're taking the union of the event that pi, the ith p-value, is less than or equal to alpha divided by m, which is going to be our new test size. All right, so this is just to be clear, we have ith p-value, and this is the adjusted test size. Okay, so now that we have that, well, what do we do? Well, what we can do is we can use what's called Boole's inequality and replace this by a summation for I in I naught, basically returning the union into a sum, thanks to a bool, I guess, less than or equal to alpha divided by m. So let me put that in here. See if I put the spelling in here. I thought I did somewhere. No, maybe I didn't. Nope. Okay. Well, I'm pretty sure it's B-O-O-L-E. Boole's inequality, if I remembered how to spell that. But now we're just summing a bunch of probabilities, and what we can get is that this thing now is less than or equal to the sum I in I naught of just alpha divided by m. And the reason for that is, I'll say because P is uniform 0, 1. So when I try to compute this probability over here, what I'm basically doing is I'm saying, well, this is the CDF of the uniform distribution. And what I want is I want to go to alpha over m, and I want to sort of add this up, and it turns out, well, it's alpha over m. That's exactly what we want. Is that? No, yeah, of course. Yeah, because it's the 1/2 base, yeah, times height. Why is that confusing me? All right, so then what we do is we have this summation over all I and I naught. So because there's no I index in alpha divided by m, we just say that this is whatever the cardinality is of I naught times alpha over m. And we know that that has to be less than or equal to m, because the biggest that the index set I naught can be is going to be m, and m times alpha over m is just alpha. And thus we have that the family-wise error rate over here is less than or equal to alpha. Yeah, something's bugging me about that triangle. Am I drawing that wrong? It should be alpha m. Something just seems... Oh no. Of course not. That's silly. I'm not... Of course. I was like, what am I doing wrong? Because obviously a triangle is 1/2 the base times the height. I was integrating it, but then I wasn't evaluating the CDF. What I should have been saying is that this is the uniform distribution, the PDF, probability density function of the uniform, and I'm just summing this up, which is just 1 times alpha over m, or alpha over m. Okay, that looks better. Sorry, that was really bugging me, because I'm like, something's wrong there. I'm combining the two different concepts, CDF and PDF, into one in my head, which is not correct. So now we're good. Yeah, so we're going to use the fact that P is uniform a lot in these methods. Now, okay, so that's straightforward, but the idea is that, so the good things is that basically no assumptions except P being uniform 0, 1. So Bonferroni's method really does apply to just about everything. The bad is very conservative. Maybe I shouldn't say that in Alberta, since we're kind of a conservative province, but yeah, the idea here is that we're not assuming really anything, and as I mentioned before, that means that we're going to have a fairly conservative test, especially when I naught, the number of null hypotheses that are true, is small. So if it's equal to m, okay, well that's good. Then this last inequality up here is actually an equality, but if only a small fraction of our hypotheses, of our null hypotheses, are true, then we're actually really over penalizing everything, because we're rounding I naught here up to m, which is could be quite a big round up. So what else can we do? Well, we have another method, and that other method, we have more than one method, but another method is called Sidex method. And this one is going to be kind of the same thought process, but we're going to have one specific requirement we're going to need, which is we need the hypotheses, the null hypothesis, or we need the p-values to be independent, or the tests to be independent for this to work. So this one, I'll say, requires that the tests, p-values that is, are independent, which is the case very often in our course, because if we have a balanced design, everything's nice and orthogonal, and our hypothesis tests will be independent, or at least uncorrelated. That's actually an interesting point. I'll have to think about that one. They're not necessarily Yeah, it's an interesting point. They will be uncorrelated, probably because they have, but then they have normal errors, so they're independent. Okay, as long as we're normal, as we assume that the errors are normal, then we're good to go. But in the case that the errors aren't normal, you could have some weird things going on, I guess, with your hypothesis tests. But anyway, save that for another course, because we're going to stick with the standard normality assumption for ours. Anyway, the idea is that for Sidex method, what we're going to do is we are going to replace the test size, I'm going to say individual, just to emphasize that we start with an individual test size of alpha, but we actually want a family-wise error rate of alpha. So we replace the individual test size alpha with, what do we replace it with? 1 minus alpha to the 1 over m. Okay, so why do we do that? Well, if we work through the math, we're going to use that and the assumption of independence in order to control the family-wise error rate. So to control the family-wise error rate, in this case, we're going to do a similar equation, but we're going to do it a little bit backwards to what we did with Bonferroni. We're going to start mathematically by saying that let's switch back to black, that 1 minus the family-wise error rate. Well, what's that going to be? If the family-wise error rate is a union, the probability that we get at least one false positive, then 1 minus the family-wise error rate is going to be an intersection. It's going to be the probability of the intersection now, I in I naught. Remember the various indices that are where the null hypothesis is true. And we're going to be taking the intersection that all the PIs for I and I naught have to be greater than or equal to this threshold 1 minus alpha 1 over m. Right, because the idea is is that what I want, or do I want 1 minus alpha over m? No, I think that's what I want. Yeah, right, the idea here is that, where is it? Let's write off to the side here. We would reject h naught I if pi is less than or equal to, well, less than. It's continuous, so it should never actually be equal to, so we can just kind of ignore that. 1 over m. So what that means is if we rearrange things a bit, what we're going to get, and here's I think I just skipped one little step here. If we rearrange things a bit, what we end up with is 1 minus alpha 1 minus m less than or equal to 1 minus, let's say less than 1 minus pi. And okay, there's one extra thing that I probably should have written here, because I realized that I'm making this in my quick write-up notes here for my lecture notes. I was being a little bit I was skipping a lot of steps, because we should note that if pi is uniform 0, 1, then 1 minus pi is also uniform 0, 1. So strictly speaking, I guess I should have a 1 minus pi in here. It's actually equivalent because pi is still a uniform 0, 1 random variable, but just to make it as clear as I can, we'll say 1 minus pi, which again is still uniform 0, 1. Oh, and I didn't close the curly brackets here. There we go. So again, intersection means all of these have to occur. Union means only one has to occur. So when we were looking at the family-wise error rate above, we said the union means that at least one of our nulls gets falsely rejected. In this case, we're doing the intersection. So 1 minus the family-wise error rate is the probability that, in some sense, none of the nulls are falsely rejected. So this is a mathematical equivalent to saying all nulls not falsely rejected, which kind of feels a little bit like a double negative, or maybe even triple negative, null not reject, and falsely. But yeah, all nulls are not falsely rejected, I guess, is perhaps the easiest way to say that in words. Now we have an intersection of a bunch of events, and what we can do is, if these are all independent, we can say that this is actually just going to be the probability, the product for I in I naught of the probability of that event, which is 1 minus pi greater than or equal to 1 minus alpha 1 over m. And this is due to independence. Okay, so we have that, and then we note that all of these 1 minus PIs are going to be uniform 0, 1. So these are, even though we have a product over a lot of probabilities, they're all actually the exact same probability. They're the same thing, because they're all just uniform 0, 1. So we end up with just the probability of 1 minus pi being greater than or equal to 1 minus alpha 1 over m. And that is taken to the I naught power, or the cardinality of I naught, or the number of elements in the index set I naught. All right, cool. And then we note that this is uniform, so it's just going to be 1 minus alpha to the now I naught over m, which goes back to that drawing that I kind of screwed up the first time, which is really just saying if I have a uniform 0, 1 random variable, and I have a point here, that's going to be something like 1 minus alpha 1 over m, then the probability of being greater than or equal to that is, well, just going to be, oh yes, because I flipped it, that's why. See, this is why I have to be really careful with my drawings, because technically I'm saying the probability being greater than it, but it's 1 minus the uniform, so it's actually, yeah, like this way. 1 minus alpha 1 over m. Yeah, because p is now flipped, yeah. Because I'm actually looking at 1 minus p. Anyway, now that we have all of this crazy stuff put together, what we can say is that the family-wise error rate is going to equal, because notice I never actually used any inequalities yet. So if I kind of undo this minus or 1 minus up here, I get that the family-wise error rate is going to be 1 minus alpha I naught divided by m. And then we're going to do exactly what we did before, which is say that this has to be less than or equal to 1 minus alpha to the m over m, because I naught can have at most n different elements inside it. And then lastly, that just becomes alpha. So once again, we show that our family-wise error rate is less than or equal to alpha. In this case, we are, I guess in this case, the good is that 1 minus alpha to the 1 over m is going to be greater than or equal to alpha over m. So better than Bonferroni. in the sense that it is less conservative or will reject more hypotheses. The bad is that we now require independence. Not a really big bad thing, but still something worth noting, which is why we still talk about Bonferroni's method and didn't just throw it out because of Sidak's method. We still keep Bonferroni around because, again, it works even in very strange cases where you have arbitrary dependencies among your hypotheses, whereas Sidak's method requires this independence. So I can break up that intersection that just fell off the top of the page there. All right. So that's two methods. Now, we're going to get into a third. And the third method we're going to talk about is called Holmes method. I guess it's Holmes's method because it's Holmes is the name. So it's Holmes's method. So Holmes's method is basically going to be a step down Bonferroni. So we didn't talk about stepwise methods. That's the next section or the next subsection after Holmes's method. But the idea is that we're going to do Bonferroni's method, but we're going to do it individually to each p-value as we go from the smallest to the largest. And we're going to change our threshold as we go. So this, in a sense, is a bit of an adaptable method, I guess you could call it, because it's going to adapt to the order of the p-values rather than just apply the same threshold to every p-value like we would in classic Bonferroni. So first, I think I used the order statistic notation. So I say first, we order the p-values. And by ordering the p-values, we end up with something that's going to look like p1 less than or equal to p2 less than or equal to up to pm. So putting the index in parentheses there is kind of a standard notation in order statistics, where you're basically saying, I'm going to re-index my p-values here so that 1 is now the smallest, m is the largest. So it's just a convenient way to do that. And then Holmes method says, so we'll say Holmes, we don't need that, says to reject h not I. I'm putting I in parentheses just to indicate that we've ordered the hypotheses so that they line up with the ordered p-values. So it says to reject that if 1 pi, well, I guess do we write the other way, or now we'll just say it this way. Actually, let's say it that way. First, 1 if we already rejected h naught 1 up to h naught I minus 1. So the first thing we have to do is reject the more extreme, the smaller p-values first before we consider pi. And secondly, we need pi to be less than or equal to, and then the new threshold is alpha divided by m minus I plus 1. Okay, so the point is that here the threshold or test size changes with I. So what that means, and you can actually plot this out if you want, is that, let's do this in, we'll do green again. So the idea is that here, let's say we have alpha, and down here we have alpha over m. And here, let's say we have 1, 2, 3, all the way up to m. Maybe we'll do an m minus 1 here, because it'll kind of explain what's going on. And this is the I-axis. So the idea here is that we would reject the first hypothesis if it's less than alpha divided by m, which is just apply Bonferroni to the smallest p-value in your set. Then if you reject that, you go to the next one and you would reject it if it's less than alpha divided by m minus 1, and then alpha divided by m minus 2, and so on. And eventually, well, actually, if we kind of cut this in half, remember m minus 1, so m minus 1 plus 1 is alpha is 2. So you end up with like an alpha over 2 here, and then you end up with an alpha for the final p-value. So you kind of get this, like, it's not a very well drawn, but it actually would look a little bit more curved than the way that I drew it. So basically the idea here is that we're going to start with the smallest p-value, work our way up, and we're going to keep increasing the test size ever so slightly with each successive rejection. And the idea, or the claim, I should say, is that somehow this is going to control the family-wise error rate. So let's see if it does that. It does, but yeah. Okay, so how do we show this? Well, okay, we're going to need some more notation here. This one gets a little bit funny. So first, what we need to do is we need to denote the index I hat, kind of a weird thing, but that's okay, to be what? This is the index such that h naught I is rejected, to be the index such that h naught I is rejected for all I less than or equal to I hat. So it's kind of the largest index that gets rejected, all right, by Holmes method. And then we want to say, also we denote I naught to be the smallest index, such that h naught I naught, I guess I should put this in brackets, should not, lots of knots here, should not be rejected. So in a sense, it's the smallest index such that h naught should not be rejected, meaning it's the largest null, or the smallest index, yes, such that h naught should not be rejected. So it's the smallest p-value. It's the smallest p-value that should not be rejected. I'll say that here, i.e. smallest p-value that we shouldn't reject. Okay, so that means, therefore, the family-wise error rate, right, is the probability, I guess what we want is we want the family-wise error rate to be the probability that no null is rejected. And in our case, in using this I and I hat notation, is the probability that I hat, the largest index rejected, is less than, strictly less than, the smallest index that we shouldn't reject, right? So what we're saying is I hat, everything I hat and to the left gets rejected. And if I naught is over here, it's the first thing that we shouldn't be rejecting. So in some sense, if that event occurs, we now have no false positives because everything we rejected was supposed to be rejected, right? Kinda? Okay. Let's go with that. So what do? What we do is we start. So now, to show that we can control the family-wise error rate, what we say is that 1 minus alpha is what? It's going to be less than or equal to the probability that Pi is greater than alpha over I naught. And this is for all I in I naught. I guess I could write it as a an intersection of events. Okay, so why is that true? Well, I naught is the number of nulls, right? So basically what I'm doing is I'm doing optimal, you could call it optimal Bonferroni correction, because if we pause this for a second and we go back up to Bonferroni's method over here said I should divide by m, but in some sense the best thing I could do would be divide by the number of true null hypotheses, which is not m. M is the total number of hypotheses, but if half of them, say, are supposed to be rejected, we'd only want to divide by m over 2 to properly correct for this, because I need to cancel out this I naught here that I'm multiplying by. So I could pick the smallest denominator possible to cancel that out, which is just I naught again. So going back down to where we are, I'm going to call this best Bonferroni. Okay, so we have that. And then the claim is that, well, since this has to happen for all I, it has to happen, since we have our p-values are ordered, yeah, this isn't equals. This just has to be the probability that p I naught here is going to be greater than our rejection threshold, right? Because what it's saying is this is kind of the, what is this? This is the smallest null p-value. So the point is that if we don't reject the smallest null p-value, we're not going to reject any others. So that's why these are equivalent statements probabilistically. Then what we have to do is say that this thing is less than or equal to the probability that p I naught is greater than alpha. And then we're going to place the I naught, capital I naught, with m minus little I naught plus 1. And why is that true? This is because I naught is less than or equal to, not less than or equal to, strictly less than m minus I naught plus 1. Okay, so why is that true? Well, if we order our hypotheses 1, H, naught 2, h naught, we'll say I naught minus 1, h naught I, and so on all the way up to h naught m. Well, remember, what is I naught? Again, the notation here takes a little bit to remember what it is. Well, it hasn't run off our screen yet. It's the smallest index such that the corresponding null hypothesis should not be rejected. And what is capital I naught? It is the collection of indices for those nulls that shouldn't be rejected. So what I'm saying is that, well, this don't reject, but all of these do reject, because this guy here is the smallest index that should not be rejected, which means everything to the left of it should be rejected. And what is to the left of it? Well, there's basically remove I naught minus 1 hypotheses. And that's exactly why I subtract by I naught minus 1 here. I'm saying that I don't know exactly what the cardinality of this I naught is, but it has to be less than that. All right, so where were we? Well, what I was saying was that we actually, I should change this to an unequal, or an less than or equals to here in green, because I'm throwing out I naught minus 1 hypotheses, but the rest of them could very well be true nulls, I guess you could say. Of course, in the probability statement, it really doesn't make any difference. Oh no, sorry, not there. It's on the other side over here, which I already did a less than or equals to. So we don't really have to worry about that too much, but just to try to be as precise as possible. Anyway, now what we've said is that 1 minus alpha, so where were we? We have 1 minus alpha on the left, and that's going to be less than or equal to, well, this probability statement, and this probability statement here is less than or equal to the probability that I hat is, or the probability that I hat is less than I naught, which, as we said above, is the family-wise, well, probability that no null is rejected, yeah, is the, well, oh, sorry, that's what I did wrong. It's 1 minus the family-wise error rate is the probability that no null is rejected. The family-wise error rate is the probability of at least one false rejection. So I had that flipped. All right. So wait, why is this last one true? Right, we always got to check these things and make sure they all make sense. This last one is true because the event that the smallest null, that is, if I naught, okay, if the probability, or if the p-value, if the probability, no, sorry, if I naught is not rejected, saying this in English is the worst, right? Basically, if I naught, if p, the p-value for I naught is greater than this threshold here, then it's not rejected by Holmes method, which means that every p-value greater than it is also not rejected by Holmes method, which means that the smallest p-value, or sorry, the largest index rejected by Holmes method, I hat, has to be less than I naught. Because we didn't reject I naught, we can't reject anything greater than I naught, so the largest rejection has to be less than I naught. There's a lot of knots floating around here, which is quite tricky. Anyway, this is a little bit roundabout, but what we finally got here, so in conclusion, we basically have that 1 minus alpha is less than or equal to 1 minus the family-wise error rate, or by flipping things around, the family-wise error rate is less than or equal to alpha. Excellent. And that is Holmes method. Now, we're not done yet, because what we want to do is consider a more general, I'm going to say more general stepwise methods. And specifically, we're going to do step down, which I always find to be strange notation because it means that we start with the smallest p-value and work our way up. And a step up method, we start with the largest p-value and work our way down. But yeah, statistics terminology, right? It's terrible. Anyway, step down method is a general approach to what we just talked about. So the general idea of a step down method is that, right, we start with the smallest p-value and we sequentially reject H naught, we'll just say null hypotheses. And then once we fail to reject an H naught, then we stop. So again, start at the bottom, start working your way up. Eventually you don't reject a hypothesis, or you reject every hypothesis, but eventually you don't reject a hypothesis, then you stop. Everything to the left gets rejected, everything to the right is not rejected. Okay. Yep, so now we can do this in general. So, and the notation's going to get even worse. Just warning you. So we're going to say let I be some subset of 1 to m. This is not I naught, but the idea is it's just some subset of indices. Then we have that H naught I is capital I. Note that it's a capital I is the joint null hypothesis. And the joint null hypothesis is that basically the joint null hypothesis is that H naught I, little I, is true for all I in I. So it's basically a way of combining a collection of null hypotheses into one null hypothesis, a joint null hypothesis. And again, people will often be pedantic and say, well, you don't want to say a null hypothesis is true. But yeah, in this case, it's just so much more convenient to say it that way because, oh man, saying this out loud is already quite hard linguistically to come up with the proper phrases. Mathematically, it's great. You just write down an equation and yeah, it makes sense. Actually saying it in words can be super annoying. Also, I should point out that this is an intersection hypothesis in the sense that I'll say i.e. H naught capital I is the intersection I in capital I of H naught little I. So it's really just saying that it's true if all of the hypotheses, the constituent hypotheses, are true. Intersection means everything has to hold. Union means just one of the things have to hold. So whenever you see an intersection, it's an and, right? It's saying this hypothesis and this hypothesis and this hypothesis and this hypothesis all have to be true if they're in this joint null. I'll say, therefore, rejecting H naught capital I means at least one H naught little I for little I in capital I is rejected. It doesn't mean we have to reject all of them, right? It just means we have to reject at least one of the constituent null hypotheses, and then the joint null is rejected. And because we just love subsets and sets, I'll say furthermore, if J contains I, so J is another index set that contains the index set I, then, all right, not rejecting, make sure I get all the logical pieces here, not rejecting H naught J implies not rejecting H naught I. Does that make sense? It does. It does, because we have to go the other way, right? The contrapositive. If we were to reject H naught capital I, it means we reject at least one of the hypotheses within that set. And since all the hypotheses in that set are also contained in J, which has more hypotheses, we would also reject J. So if we contrapositive it, it says if we don't reject J, that means we can't reject any of the hypotheses inside J, and all of the I hypotheses lie within J. Good? All right. This is a big leap up from what we were doing before, where I was just writing down a hypothetical experiment and coming up with some arbitrary framework, like, oh yeah, it's medical trials or someone walking around in a field. Now we have to do a bunch of sets. All right, so now the claim is that, so we assume that for every subset I of indexes, that we have a, I'm going to say size alpha or level alpha, I'll say non-randomized test function. There's some good statistics jargon for you. Non-randomized test function, which is the fancy way to say that we have a phi x semicolon I, which is going to equal 0 or 1. So non-randomized test function is just the fancy way to say, okay, I got some function, it's gonna basically equal 0 or it's gonna be 1. And the probability that phi x, I hate x here because x doesn't really mean anything, but we'll just stick with the notation. H naught I is less than or equal to alpha. Okay, so this is the whole size alpha bit, is this statement. So it's the
fancy way to basically say, if you get a 0, you reject if you get a 0, you don't reject. If you get a 1, you do reject. And the probability that I do reject, given that I shouldn't have rejected, is alpha. So the assumption is that we have some non-randomized test function. So the example to make this a little more tangible for, let's say, Bonferroni is reject if the p-value is less than or equal to a over the size of I. So that's really all it's saying. It's kind of like fancy notation, but really all it's saying is, okay, when do I reject? Well, in the Bonferroni case, if I have cardinality I hypotheses, I would reject if my p-value is less than alpha divided by I. So that's all it's really saying. It's just, a fancy way to write it, and a more general way to write it, I guess. Because then we can define, so we define a simultaneous test function which is going to be capital Phi, and capital Phi x I says return the minimum of, I guess, all j that contain I of phi x. This is terrible notation, right? I mean, it's clean, but it's just a lot. Okay, so what in the world does that mean? Well, remember, the simultaneous test function is still just going to be a 0 or a 1. And what it's saying is take the smallest value of 0 or 1 over all possible sets j that contain I. So what does that mean? It means that, therefore, we reject H naught I, capital I, at, we'll say, level alpha only when all H naught j are rejected at level alpha. So in some sense, we're kind of, if we were to think about this in the stepwise approach of Holmes method that we already did, the idea is that, okay, we start with, in some sense, all of the hypotheses, all m of them, and if we apply Bonferroni to all m of them, we take alpha and we divide by m, right? And then we would reject that simultaneous hypothesis. We throw out the smallest p-value if we reject. Then we now have m-1 hypotheses. We have a smaller set of indices, 2 to m, and then we would take alpha and divide by the new cardinality, which is m-1, and then we would continue onward in our step-down approach, which goes in an increasing way, because of course it does. Right, so really got to talk to the people who invented this stuff, right? I mean, ugh. All right, so what that means for us, for our purposes, we're almost there now. For our purposes, we have, remember that I naught contains the true, null indices indices. I guess it's the same thing. So therefore, for any I that is contained in I naught, which means that now I, no subscript, is going to contain only true null hypotheses, then if the probability of little phi I naught, I completely messed that up. Little phi of x, for whatever x is supposed to be, I naught, is equal to 1. The probability that this is equal to 1, which is that we reject the joint hypothesis, which is we make a false rejection less than or equal to alpha, then the simultaneous hypothesis, this crazy capital phi of x I is equal to 1 is less than or equal to alpha. So this guy here is really just the kind of the family-wise error rate expression. What it's saying is that the probability that we reject at least one of the null hypotheses is less than or equal to alpha. If that's true, then this kind of abstract notion of a simultaneous test function will also have the probability of that equaling 1 will also be less than or equal to alpha because of the way that it is defined up here, in the sense that it has to be the minimum over all j that contain I, and I naught contains I. So the probability can only get, it still has to be less than alpha, I guess, because of set theory, perhaps, the fact that we have nested sets. All right. So what that means is that, therefore, this capital phi simultaneously controls the probability, simultaneously controls the probability of falsely rejecting any H naught I for I containing I naught. So in this case, this is a test. It's a rejection. It's basically the simultaneous test function is saying, how do we choose to reject? And what we're saying is that this will have the correct rejection rate for any collection of null hypotheses. So this is a really, really abstract way of saying, if we have a nice test function phi, little phi, then we can create the simultaneous test function capital Phi that will control what we need to control in this step down way. So what that means is basically, in a nutshell, define a phi, e.g. Bonferroni, alpha over the cardinality of I, then we construct a capital Phi, which is, in this case, let's say Holmes, which is alpha divided by m minus I plus 1 or whatever, something like that. So that's what this whole crazy abstract diversion is telling us. It's saying if I have a way of controlling the family-wise error rate for a collection of hypotheses, I can translate it into a step-down procedure with this approach. Of course, just writing this all down, the thought is now how in the world am I supposed to translate this? So we'll do an example and then we will stop this lecture because we're getting a little bit long here, but that's okay because I want to wrap up this this topic. So, okay, so let's, for convenience, so assume that P1 is less than, or I guess less than or equal to P2, even though they're never going to be equal for continuous, I guess. Let's assume we have that set up. I'm just going to drop the parentheses because it gets kind of annoying to also include parentheses everywhere. And then we denote I sub little I. Again, not the greatest notation in the world, but it'll do. All right, so now we have our I sub little I, which is all indices I plus 1 up to m. Therefore, and the cardinality of this set is going to be m minus I plus 1. Hence, applying Bonferroni to I sub I means rejecting, we'll say H naught K if, let's say, or I should say for K greater than or equal to I, if the p-value P sub K is less than or equal to, I think I should say strictly less than m minus I plus 1. This is just Bonferroni. We're not doing Holmes yet. What I'm just saying is that if I take a collection of m minus I plus 1 p-values, then Bonferroni says I should reject if my p-value drops below alpha divided by the total number of tests. So this is just Bonferroni applied to a subset. I should write that in blue. Bonferroni applied to a subset. In this case, specifically I sub little I. And what we would say is that since the p-values are ordered, we would reject the entire joint hypothesis H naught capital I sub little I if P sub I, the smallest p value in that set, is less than m minus I plus 1 as, oh, and that's the next step. Okay. Now, furthermore, we can say that since IJ contains I sub I for any j less than or equal to I, we have the simultaneous rule. The simultaneous rule, which is, I'll write it in green, reject H naught I sub I only, let's get rid of that mark, only if we reject H naught I sub j. This is for all j less than or equal to I. So this is that idea of a simultaneous rule. This is the great capital Phi that I was talking about. And this is equivalently, so this is, I'll say equivalently, well, reject H naught capital I sub I only if Pj, so wait, why would we reject H naught I sub j? Well, we'd reject H naught I sub j if Pj is less than alpha over m minus j plus 1. And this is for all j less than or equal to I. And this is Holmes method. Okay. So is it clear what we did here? Because it's a little abstract, so it may not be immediately clear. But what we basically did was we said, let's start with Bonferroni. Bonferroni is little phi. It's just a way to determine if we should reject p-values given a set of p-values. And then the idea is that if we apply that to a collection, a joint null hypothesis, and then we consider the simultaneous test, which is that we have to reject all of the larger joint nulls first, then what that gives us in this specific setting is Holmes's method. So it's basically saying, well, if I want to consider rejecting I sub I, the ith p-value, I should already consider the bigger sets, which are the I sub j's, which contain more p-values because j is less than I. Okay, so hopefully that actually makes a little bit of sense. It's a little bit confusing to say out loud, and it would be a lot nicer if you were sitting in front of me so you could just ask me a question if that didn't make any sense, because saying things like I sub j naught is less than j sub I naught just sounds really weird when I'm speaking into a microphone. So definitely talk to me, send me an email, let me know if this makes any sense at all. And what we're going to do in the next lecture is we're going to talk about the false discovery rate. That's going to be a shorter lecture than this. And then we'll follow up with some examples in R to try to solidify what's actually going on here, because luckily all of these methods can get wrapped up into one R function called p.adjust, and we can look at that and do some tests to see how it works in practice and what sort of success we get with actually rejecting null hypotheses and controlling family-wise error rate or the false discovery rate. So stay tuned for that. That'll be the next lecture, and I will see you there.